So many ionic compounds have crystalline structures that are closely related to the unit cells, but the complicating factor here is when you have an ionic compound, you have at least two different ions, right? So you can't just look at, oh, these are all the same element. Now we have two different elements, and so we have issues of different sizes. We also have issues of charge neutrality. So sodium chloride, you have one ion of each kind, but something like calcium chloride, you have twice as many chlorine ions as you do calcium. So coordination number here isn't atoms that are directly contacting each other, but it's the number of close cation-anion interactions. Those are the attractive forces, and that will lower the potential energy. In general, if the cation and the anion are more similar in size, you'll get a higher coordination number. If they are very different in size, you'll have a lower coordination number. So we're going to look at these very generally. So if we have ionic solids where the ions have similar size, an example of this is cesium chloride. And so this will make a simple cubic cell. So the chloride ions are at the corners in the green. And the cesium atom has to fit in between. So the cesium atom is going to go in the middle of this. This is not a body-centered unit cell, because when we define the unit cell, you can only look at one kind of ion. So just looking at the green ones, this is simple cubic. The cesium atom goes in the middle. The green chlorides, within the unit cell, there's the equivalent of one chloride ion and one cesium ion. Coordination number here is 8. Things like calcium sulfide have a similar structure. If we looked at something like sodium chloride, where the sodium ions are significantly smaller than the chloride ions, if we didn't have to worry about charge, if we only looked at ion size, we could fit a lot of these little purple balls around the green ones. We wouldn't have to have a 1-to-1 ratio. We could fit a whole bunch of these in there and pack things in tighter. But we do have to consider charge neutrality. We have to have an equal number of sodium and chloride ions. So what happens is that each sodium ion has to be surrounded by an equal number of chloride ions. The chloride ions end up occupying a face-centered cubic cell. So here the chloride, this is one face. So we have a chloride ion at each corner and one at the face. So a face-centered is going to have a total of 4 ions or atoms in it, right? So then this cell has 4 chloride ions and 4 sodium ions. The chloride ions are parts of ions. We've got half of this one and half of that one. Here we have 1 sodium ion in the middle, and then these guys, we're going to have parts of those as well. It's going to add up to 4 of each. This is called a rock salt structure. If the size gets even larger, then the coordination number drops to 4. This is called the zinc blende structure, after the mineral zinc blende, which is a zinc sulfide. So we have the sulfide ions, the large ones, occupying a face-centered cubic structure again. But now the zinc ions are in what are called the tetrahedral holes between 4 sulfide ions. So if we look at 4 of the sulfide ions, they form a tetrahedron, and in the middle is called the tetrahedral hole. So this one, that one, and that one, that's 4 sulfide ions forming a tetrahedron, and there's a zinc in there. There's actually 8 tetrahedral holes that are formed inside this cell, but there are zinc ions in only 4 of them. Because you have +2 and -2 charges, you have to have equal numbers of sulfide and zinc ions. You can also have ionic solids with unequal numbers of ions. An example is calcium fluoride, where you have 1 cation to 2 anions. And this will adopt the fluorite structure. Calcium fluoride is fluorite, where we get the calcium ions occupying the lattice points of a face-centered cubic, and the fluoride ions going in the tetrahedral holes. Since we need twice as many fluorides as calcium, they will occupy all 8 of the tetrahedral holes. There's also an anti-fluorite structure, which is used when you have 2 cations to 1 anion. So which of these compounds is most likely to crystallize in the zinc blend structure? Well, what the heck was the zinc blend structure, right? Let's go back and look at that. So this is our zinc blend structure, and when we're talking about this, we're saying that it has a large size difference, and this is also a 1-to-1 ratio, right? Equal numbers of cations and anions, but large size difference. So if we go back and look at this question, we're looking for an ionic compound that has a 1-to-1 ratio. So can we eliminate any of these? Magnesium chloride, that's got a 1-to-2. That can't be the zinc blend structure. It's got the wrong ratio. So now we're looking at rubidium chloride and copper iodide. And so what we're going to do is we're going to look at which one has the biggest difference in size between the ions. So here we have 148 and 181. Here we have 96 and 216. So even without getting out your calculator, this is smaller than the smallest, and that's larger than the largest. So this has got the biggest difference. So we would choose this one based on the size difference.
So whichever has the biggest difference is.
Yeah. The zinc blend is for a 1-to-1 ratio with a large size difference. When the size difference is not very big, then you have something like this, the rock salt structure. Questions like this are going to come up in homework. I try to be really, really careful with exam questions about this because the details of which structure it is, I don't feel are a critical part of general chemistry. We need to talk about them. You need to know that they exist. If you go on and study geology, you're going to learn a lot about this. This is the reason different minerals have different shapes. Some of them make little, table salt. You go home and look at the table salt. Spill some on the table, put the salt on the table, right? And look at it. It's little cubes. Do you think the Morton Salt Company puts a great deal of effort into making sure that each piece of salt is cubic? No, they don't. It naturally forms that way. Other minerals, because of how their atoms or their ions arrange due to size difference and charge balance, will form maybe orthorhombic structures. And so you look at their crystals, like, I don't know if you remember on Monday, those sodium thiosulfate crystals had kind of a distinctive shape, right? It's because of the relationships between size and charge balance and how they interact with each other. That determines the shape of the crystal. So I think it's important to have heard about this. I don't think it's important to be able to answer a question like this without some sort of reference material. Okay. So a good way to know what should I study for the exam is to look at the practice exam questions on Master in Chemistry.